Hello, welcome to episode number 2 of Chemistry Revision. Today we're going to be covering VSPER Theory, the valence shell electron pair repulsion theory, even though I've missed out the E on my title, and clearly my entire Y. This theory allows us to deduce shape of geometry of the molecules by using electron repulsion theory, along with just some general other rules that we should follow to get our 3D shape in geometry. This is a pretty key topic because this essentially outlines why we have a 3D model and why the molecules are shaped in that way. So what I have on my whiteboard is how you use the VSPER theory. I just wanted to do some quick little principles first that I obviously didn't write down because I'm an idiot. So our first core principle is this entire model is built around electrons and how electrons move, shown here. So let's say we have, I don't want to rub this off because it took me a little while to write. So we have carbon. Now obviously carbon has 4 outer shell electrons. So 4 sp3 bonds that can be made, essentially, but we'll get to that on later. Carbon has 4 outer shell electrons. These 4 can be used in many bonds, forming single bonds, which you see in your alkene chains. You find double bonds. If you're lucky, you can even find triple bonds. Sometimes, well, to my knowledge, carbon bonded 4 times to another carbon isn't a very good idea. I don't even know if it's possible. So a diatomic carbon is essentially just a theory. So we don't really get it. It is obviously around the fabled quadruple bond, but again, we're not going to cover that in today's video. Now, when I say VSPER theory is based around electrons, I'm more talking about valence electrons, which you'll see me use a lot, and lone pair electrons. Now, valence electrons are our outermost shell electrons, so all the electrons we find on the outer ring, so on our p orbital, say, on our s orbital, say, wherever you are on the periodic table. These electrons can be used in bonding, but they can also be used in lone pairs. So if we take a look at oxygen here, oxygen has a lone pair, another lone pair, and 2 single electrons. These are all valence electrons as they are on oxygen's outer shell, to say. Now, when I talk about lone pair electrons, as I just said, with oxygen, these electrons aren't used in the bonding we're going to cover today, but they are used for repulsion. So as you can see in number 4, when I say electron rules, the rule essentially is electron minus does not like electron minus. So these two will want to be as far apart as possible. And because a lone pair has 2 electrons, they're going to push other electrons further than a single electron would. And that's all I mean. Now, because the lone pair pushes the single, well, not a single electron, but a single pair, or a bonding pair away, shall we say, the lone pair ends up decreasing bond angle. And once we go through the rules, I'll make an example of this in carbon dioxide, and we'll use methane. Why not? So that's what I mean by valence and lone pair electrons. They are everything that is covered in VSPER theory. The rest are simply what you have to do to follow. So we'll go to rule 1. First thing we need to do is identify the central atom. What I mean by that is, let's use methane. That's not methane, that's a methyl ion. We'll use methane. How do we know that carbon is our central ion? Because hydrogen only has the 1 electron to bond with, which is a little bit silly. So hydrogen can't make 4 bonds, as it only has 1 electron. Whereas carbon has 1, 2, 3, 4 electrons, meaning this has to be our central ion. Our central ion can change depending on what molecule you have, but how I like to look at it, this can only form 1 bond for every 4, this can make 4 bonds for every 1. So identifying our central ion, we know that that's carbon. Now a little note, as said before, our central ion is usually the one that's least electronegative, or most electron positive was probably what I was going to say. Just as a little heads up note. Now our second rule of VSPER theory and how we use it is by counting our valence electrons. So we have to count the outer shell electrons on all of our atoms. So on our carbon and on our hydrogen. On our carbon we have 1, 2, 3, 4. So C equals 4 valence electrons. I'm just going to use V for valence because I really don't have a lot of space. Now for hydrogen just has the 1. Equals 1 V electron. Next, we identify whether our valence electrons are bonding electrons or whether they are lone electrons, also known as a lone pair. So 4V, 1V. In methane, carbon is using 1, 2, 3, 4 of its 4 bonds for bonding, as there are 1, 2, 3, 4. So these are all bonding, and these are also bonding. And then to make this into 3D, we move to the fourth step, which is apply our electron rules. So let me quickly draw this in 3D, 2D again, so we can see everything like that. So we've identified our central atom, which is carbon, and now we need to find a shape that it obeys and find our angles. So there are no lone pairs, so our angles are still. So our angles are going to be what's the word I want to use? I can't remember the word I want to use. So from this point, I begin to start forgetting what I was going to say. Please be warned, this does happen a lot. And just for your entertainment, here's the lullaby back. I'm having a brain fart. How am I having a brain fart? So this shape, we'll move on from electrons completely, I think, for now. So the shape of this, because it has no lone pairs, is going to be this, where our slash line means it's going into the page, and our wedged line, you can see that okay? Yes, you can. It's out of. So to give a visual, something like this, where we have one hydrogen going up from the carbon, and then 3 hydrogens, one here, and one here, coming down and away from and into the camera, shall we say. And as you can see, all of these are the same distance away from each other. So from here to here is exactly the same as here to here, as the electrons are the furthest away from each other, making this molecule stable. It's time to remake my lovely little molecule that I can't remember the name of, but we will move. Let's try with another molecule. This time I'll throw in some lone pairs. So Bi3. Here is our central atom, as this is less electronegative than this. Again, following the usual electronegative rule. Boron has 3 valence electrons, as it's in group 3, whereas iodine has 7. If we look at our outer shell for iodine, however, you'll see that there is 1, 2, 3 lone pairs, which means that iodine only has 1 bonding electron. So, taking this all into account, we have our central atom and our 3 atoms surrounding it. And to throw this into 3-dimensional space, we're going to take into account lone pairs. You know what, I'll just rub it out and do it again. How I like to start is I always like to put a bond above, just so then I can map in my brain how they're going to bond. Now it needs to be even on both sides so that both repels. So this way can repel as much as this way. And these repel in the same manner, giving us oh, I have a triple lone pair, that's silly. Giving us this structure. Now I've made an oopsie with my drawing, so I'll put my other lone pair down here. There are probably easier ways of doing VSPER theory while taking account in the lone pairs. So when you come to other central atoms, like nitrogen, which I will have a brief run through now, using ammonia. Our central atom, our nitrogen, has 5 valence electrons. 1, 2, 3, 4, 5. Now, as you can probably already tell, there is a cheeky lone pair. So nitrogen has 5 valence, but also has 1 lone pair, meaning nitrogen has 3 bonding pairs. This one, and this one. Our hydrogen is exactly the same as before, is exactly the same thing we did with methane. It's a methyl ion, what am I doing with myself? Both have 1 valence, 0 lone pair. So the only thing that's going to be affecting our bond angles is this lone pair, making this our 2D structure, and this our 3D structure. The reason it's shaped like this is because this lone pair is essentially acting like this hydrogen on methane. It's acting like this, except in this scenario, the repulsion is a lot stronger than the hydrogen on methane. So I'll show you in 3D again. If I can draw in 3D. Now you see that they both have similar structures, and that's because they're both tetrahedral. I actually lie, they're not both tetrahedral. These has a bond angle of 109.5. I'll just write 109 because I'm lazy. And this has a bond angle of 107.5. Because of this lone pair, our bond angle decreases. Simply because lone pairs are stronger than bonding pairs. And there we have it. That is VSPER theory. Hopefully some of you understand the thoughts, understand the process. I don't think I've explained it justice, but using this sort of theory, you will be able to at least attempt some VSPER theory questions. Just remember, lone pairs decrease bond angle. Thank you very much. So that's all the teaching and the revision, if you want to call it, for this video. I just wanted to take your attention over to the aims of this, whilst you stare at this lovely sunset and hopefully some other pictures that I throw in. This is going to be a recurring series because it helps me revise, and I hope that in helping you revise, I help myself. So, yeah. Hopefully you guys understand everything that I say. If you need any help, please don't be afraid to comment. I will always keep an eye on my comments. Thank you so much for watching. It means a lot that you're taking an interest, and hopefully we'll see you in the next one.